Okay, today we're going to look at equations of motion, cylindrical coordinates. Now, the coordinate system is really essentially the same thing as what we had done in Chapter 12, Section 8. So you will find to at least the form of the acceleration, the two acceleration uh, components will be the same, essentially the same way we found it in um, Chapter 12, Section 8. So we're not going to go through and derive that. We're more or less going to start applying it, okay? Now, we'll look at some potential applications here. Now we're talking about, in the previous chapter, chapter 12, we had kinematics. Now, that was just describing motion. Now we're dealing with kinetics where we actually have to think about the forces that are involved with that motion, okay? So, for example, in the first example here, or at least the potential application, um, if you were looking for a specific force, in this case, a frictional force, you could actually solve it through using the cylindrical coordinate system, right? So we'll actually take a look at some problems, but something like this could be a potential problem that you might want to look at, okay? Now here's another one. Here's another application. And in this specific application, um, maybe you want to figure out uh, the centrifugal force causes the normal force in this case. How would you figure out what the velocity is necessary for the pilot to experience weightlessness? And really, essentially, what you're going to find is that the centrifugal force is essentially going to equal to the weight of the pilot, right? So um, when we're talking about being at this point in the loop, at the top loop, part of the loop, okay? And what you're going to see is that, in this case, you have an R um, defined, relative to some, instantaneous radius, in this case, an actual radius, at least for the point we're talking about this, and an angle relative to something. In this case, it's relative to the vertical. The applications we're going to look at, it's going to be relative to the like positive x-axis, if you want to think about that, or even I shouldn't say positive x-axis, but only in certain cases it's positive x-axis. Otherwise, it's relative to the r um, um, vector at that point in time. Okay. All right. So cylindrical components. What we're going to find is that we have a component UR, the R direction, and one in the theta direction, and another one in the Z direction. Okay. Now, for the problems that we're going to look at, and I don't want to say for sure, but pretty much we're going to be looking at two-dimensional problems. Okay. And when you have a two-dimensional problem, of course, then you don't have the z component, and you simplify it into the plane made by these two vectors, these two unit vectors, UR and U theta. Okay. Well, here's just the general form of the equations, right? And if you recognize here, AR was what we had found in previously in chapter 12.8, and also A theta, we also found that. So really, the part that we're adding to this is we're essentially, summing the forces are going to equal to the mass times acceleration in this case. Okay. All right. Okay. Now, in this case, here's the example where you have it in just the r theta plane, then you just don't have a z component. And that's really what we're going to be looking at here. And I think the first few examples will have that. Okay. All right. Okay. So this one is going to be, we're using an actual fixed coordinate system. All right. All right. So let's take a look at this and kind of see what this means. One of the things we're going to recognize here is that, you have r, which is some function of theta. And theta itself is a function of time. It doesn't really, the author doesn't really show it here, but what we're going to recognize is that, we're looking for time derivatives, and theta is going to be a function of time, right? It's really the 2 pi f times the time. Okay. All right. So one of the things that we're going to look at is this idea of we having this angle psi. Okay. Now there's a relationship between psi. If you think about like how this rotation happens and how you're moving, how this actual point or particle is moving, um, and this is a good description of it. So the basic idea is here is that if you wanted to think about in terms of the relationships, now these were what we had gone through and talked about back in chapter 12, section 8. And if you think about it, if you're looking at the relationship, tangent is just basically, the opposite or the adjacent. And the angle that we're talking about really is right here. Like here's our opposite and here's our adjacent side. And psi actually is right here. And if you notice that essentially if you think about like these two lines being parallel because it's such a small amount, if you this being r, also these both being the length of r, is that what you're going to find is this angle essentially in here is really just this line is splitting the two parallel lines, which is this angle here, psi. Okay. The author presents this here. It's just sort of conceptually seeing how you have these relationships. Um, it's good just to have a general idea where this is coming from. Okay. Okay. Oh, and in terms of the direction also, right? It's measured counterclockwise from the radial component. It's going to be positive, and if it's going clockwise, so if you're down here, let's say, then you would say it's negative. Okay. Okay. So here's the first part. We'll take a look at an example. And what we're looking for in this case is we're going to look for the force acting on this arm here. Okay. And we're starting off at some point, and what we're saying is essentially when theta gets equal to 0. So if you look at the sign on this is the angular velocity. If you look at the sign in this, what is essentially saying, we have theta go in the positive direction. This thing is moving basically, or not positive direction, but this is essentially moving. Theta is in the counterclockwise direction relative to the horizontal. And this motion is actually opposite that, right? So that's why it's a negative sign here. So it's going from here down to that, okay? So we're looking at it, we want to find it when theta essentially is equal to 0 degrees, okay? Okay. So the approach taken here is, we come up with our free body diagram and the kinetic diagrams, and such as in class, and we had talked about it. The kinetic diagram and free body diagram can be together if you want, and that's often done. In this case, the author chose to do it as a separate. Okay. The next thing is we're going to have our, we got the free body diagram, kinetic diagram, and then we're going to go through and look at coming up with the equations for this, right? And really, the equations come from this, from the free body and the kinetic diagrams. Okay. So we'll come up from that, right? We'll actually develop the summation of the forces in a certain direction equal to mass and acceleration and any other forces that are involved. But it's really coming from the free body diagram and the kinetic diagram. Then, in this case, you're just going to apply it. You're going to substitute in for, theta equal to 0 degrees to come up with the equation for the motion, or to find the force. You got to come up with an equation for the motion, then you're going to use that to find the force. Okay. Okay, so here we go. First part, free body diagram. So what do we have? We have a normal force acting essentially at the bottom part of this bar, pushing back up against this P point. I forget, pin. It's a pin. That's what it is. A pin. And then you have acceleration essentially in two different directions. And we're defining this as being positive, going up in the positive theta direction, and MR going out. So this is the typical way we would define it, is for relative to our coordinate system defined here. Okay. So the next thing is that we need to actually, if you look back at our equations, of course, what do you need to do? Well, you need to find the second time derivative with respect to r, second time derivative of r with respect to time, and then the the first derivative of theta with respect to time, and then the second derivative of theta with respect to time, first derivative of r with respect to time, and second derivative of the theta, first derivative of theta with respect to time. So you need to find these individual components here, okay, and then we can solve for it, right? Okay, so let's go back where we were. Okay. Okay. So we have our free body diagram and our kinetic diagram. Okay. So all right off the bat, we know we need to find A theta and AR. Okay. So looking at this, we're looking for, um, our first time derivative and the second time derivative here. And then also, of course, we need to do it for theta, which is really going to be pretty straightforward, right? Because we've already given at 0 degrees, you can solve for this. Of course, we're given this. This is the angular velocity. And then, of course, the time, this is a constant. So the second derivative of theta with respect to time is essentially 0, okay? But the first one here, if we want to take a look at this in a little more detail, we can do that. And just to look at this, kind of where this all comes from. And so the first part of it, we can use the general form for the trig functions. This first part here, we use the general form of the trig functions, which is essentially using the chain rule here. Okay. Where in this case, we're defining u as being this term right here, 2 theta. Okay. So if we do the derivative of this, essentially using this form, just going to have minus 0.6 because it's a minus sign, and then u, and then we do the derivative of du, which is just 2 times theta with respect to time, right? D theta with respect to time, dt. So when we do that, of course, all we're going to have, and we write it in the form of the dot form, we're just going to have minus 1.2 sine 2 theta times theta dot, okay? For the second one, when we're trying to find the second derivative of r with respect to time, we're going to apply the product rule and the other trig function. And when we do that, essentially it's like, what do we have? This is essentially my u, this is my v, okay? So this is my first term of function of theta, this is my first function, and this is my second function. So when you do that, what's going to happen is here's my u, and then my second function, well, my u is here. So the second one is just going to be d theta, the second derivative of theta with respect to time. Okay. Then this one, v is essentially this. And then you're going to do the derivative du, which is essentially this is u. This whole thing is u. And in this case, if you're following what I used, my substitutions I used in this form. And the second part is that you're applying this. Oh, I don't know, maybe I should have used something different than u. I kind of reused it here and here. What you recognize is this maybe is v, or not v, but maybe w or something else, some other variable. So when you do that derivative, what you're going to end up with is another 2 times first time derivative with respect to time, because essentially I'm just doing the derivative of this thing right here, okay, 2 theta. Okay, and then when you just go and multiply 1.2 times 2, and then you multiply this dot theta times this dot theta, you come up with theta squared. Okay, so this basically gives you an idea of where this comes from. So when you see this form of these equations, that maybe give you a little bit of an idea. I filled in a little bit of those details. Okay. As I said before, right from kinematics, and this is, from the kinematics too, this is also what we had found, is that you just have, the first derivative, which is given. This was our given component. And then, of course, this is a constant, so the second derivative is, with respect to time, is just going to be 0. Okay. So all you have to do is substitute in for theta as 0 degrees. And when you do that, you come up with a value for r. You come up with a value for r dot, or r with first derivative of r with respect to time, and r double dot. And this is where you have, we come up with actual values, all right, for each of those. Now you just take those and substitute them in to our equation for our acceleration in the r direction and for our acceleration in the theta direction, okay? And let me go back to this. Okay. And when you do that, what you're going to and then after that, this is actually this should be theta. It's actually it's written as this. It'd be theta, a theta. So you're going to have what you're going to recognize here is that in that direction, in the theta direction, you have 0 right here. So yeah, this should be theta. I just noticed that. This should be theta, a theta. So writing out the equation, this is basically the summation of all the forces, right? This is our normal force, and then gravity, right? This is from our free body diagram. And this is in the theta direction, so that was this. Okay. And so what you're going to find, and there's really nothing, in terms of, we're looking for the force that the bar is acting on it. So that's the normal force. So we have a normal force, and here's our force acting down due to the weight. And here's our mass times acceleration. What we recognize that in the theta direction, this is theta, theta, this is 0. So our normal force in this case is just going to be, it's just essentially the weight of that object. Okay? So that's how that problem works out. Okay. The second one is similar kind of a thing as what we had previously. This one is just that we have a mass, and now we have another function, and this function is a little bit different than the first one. And, we're given some quantities here. Oh, here's the quantity. Here's the angular velocity. And it's the same thing. In this case, it's going in the other direction. So now we're positive theta. And we'll follow the same approach. In this case, r is defined essentially from, we already have it defined from here, from a origin. So this is from this point here. Okay. And when we do that, same thing, you can, in this case, the author did a little bit different, but essentially you could do, it's the same approach. You can do free body diagram, kinetic diagram if you want first. And you're just looking for the acceleration components using the kinematic equation. So it's nothing, there's nothing different essentially from what we had previously done. Oh, the derivative is a little bit simpler now. You just have theta, so then it just becomes theta prime. And you do the same kind of thing here as what we previously did. Okay, you use the same approach to find the components. Okay, same thing. You have an angular velocity. Now you have an angle 30 degrees that you're going to find it at. You have an angular velocity, then the second derivative, same thing. Your angular velocity is constant. So then, of course, the angular acceleration, sometimes you'll see this as just like alpha, right? So the angular acceleration is 0 for this case, okay? So when you substitute in for each of these, what you're going to find is going to be, r is, when you put in 30 degrees, you're going to find r is 1.039. The first derivative of r with respect to time is minus 0.3 meters per second. And the second derivative with respect to time is minus 0.2598 meters per second squared. Okay. Now you just take those values and you plug them back into our equations for, our AR, acceleration R direction and acceleration theta direction. And you come up with these values. Okay. Now, the author took a little different approach in this case and went through and defined the free body diagram, kinetic diagram, originally second instead of first, which it really doesn't matter because what you recognize is this is like, you need to find these. You need to find the derivatives of each of these, the second derivative, and also of theta also, because we know we need those when we actually plug in for our accelerations in our standard equations that we had from kinematics. Okay, so what we're going to have is we have a normal force. So if we look back, we'll look at, this is the normal force of the actual object that this, what did we call this? This is a rotating rod, where it's actually the surface that it's actually rolling on is the normal force. And then the force of the bar pushing on it, and then here's the weight. So these are the three forces that are acting in this particular problem. Okay. Okay. So all we have to do is we go and substitute in. So here's our forces, right? We need to break these up into our components, right? So our essentially our our y, our x components.